Hello, and welcome to Astronomy 100. In this last video in this series, we're going to talk about the last bits and pieces that go along with orbital mechanics. And what we've seen so far is that there's a lot of components to this that when you bring them all together describes what it means for one object to orbit around another one. So let's go ahead and get back into putting all this together. Now, in this splash screen that we've been seeing over and over again, now we can talk a little bit more in detail as to what you're seeing. So this is the International Space Station. And the International Space Station obviously orbits the Earth continuously. And the altitude, or how high up above the surface of the Earth that the space station is a couple of 100 miles above the surface of the Earth. Now, there's a reason for that, and we'll get to that in just a second. But remember, an orbiting body is a falling body. And so the space station is continuously falling around the Earth. The reason why it doesn't stop and it's able to keep falling is because there's nothing to stop it. Remember Newton's first law is that a body in motion will continue in motion unless acted upon by an outside force. So the speed of the falling space station is the same speed it always has because there's nothing to slow it down. It just continuously falls around the Earth. The moon is also doing the exact same thing that the space station is doing. The moon is also falling around the Earth, and it falls with a particular speed, so it has a speed as well as falling, and you combine those two, and the moon orbits around the Earth. So all orbiting bodies are falling bodies. Now, we saw in the last video the minimum velocity or speed to be able to fall around the Earth and not hit it if you're in the low Earth orbit, very much like the International Space Station, is 17,500 miles per hour. So what that means is the International Space Station is falling at 17,500 miles per hour, and when it goes at that speed, the force of gravity pulling on it curves the fall so that it orbits the Earth. Now, how do we get to 17,500 miles per hour? We saw in the last video that airplanes just don't do that, but obviously spacecraft, spaceships can do that. Here is the now retired space shuttle, and this was a photograph taken during a night launch. So this is from Florida, and they would frequently launch it at night, and when they do launch it at night, it's quite a spectacle to see. What I want you to notice, though, is the space shuttle is pointed upwards. And a common mistake that people make is they think that the shuttle is pointed up because the goal is to get into space, which is above us. But that's actually just convenient for it to be on the launch pad in an upright position. Once they light the engines, what happens is the shuttle lifts off the pad, and it is indeed going up. But what you can see in this photograph over here, this is an image taken by somebody standing miles away, but it's a timed exposure, meaning that he left the shutter open for a few minutes, and you can see the trajectory of the space shuttle. And notice that it rises up, but after about a minute, it starts to curve and it starts to go more downrange. In other words, it is starting to go horizontal, mimicking the curvature of the Earth. So they're not trying to get up into space and go away. What they're trying to do is to get up high enough so you're out of the atmosphere so that the atmosphere won't slow you down. The wind resistance pushing through the atmosphere would slow you down. But they're also trying to go to the speed of 17,500 miles per hour. So it goes up and then over, and then it's now more going horizontally than anything else. And once the shuttle is going faster and faster and faster and faster, they watch the speed, and then once it reaches 17,500 miles per hour, they turn off the engines, and then the shuttle simply falls. So this is the orbiting space shuttle. Notice the engines are not running. Notice that the shuttle is just falling. And as long as it's out of the air, couple of 100 miles up, get out of the Earth's atmosphere, the shuttle will just continuously fall and then essentially never hit the ground. So the shuttle is able to achieve that speed, and the way that it's able to get to that speed are the very, very big engines that are attached to the rocket, as well as the shuttle's engines, so that it can finally get to 17,500 miles per hour. So the space shuttle and the space station and the moon, everything is falling while it orbits. Let's tie all this together. So let's use the moon as our example. The moon is going around the Earth. Here's the orbit of the moon. We'll make it very simple here. Now don't forget, there is the force of gravity between the moon and the Earth. In other words, the Earth and the moon are trying to pull themselves together. The moon and the Earth would eventually come together if we left them alone. But instead of just simply leaving them alone, let's give the moon a particular speed. So it has a speed in one direction, and if we were to be able to shut off gravity, what would happen is the moon would just follow the yellow arrow and keep on going. So without gravity, the speed of the moon would just go, and it would leave. And it would leave our solar system and go away. But of course, there is gravity. We can't shut off gravity. And so when you combine gravity, the force trying to pull the two together, with the speed of the moon, that creates a falling action. The moon is going to fall, but combine it with its speed, and that means you get a curved trajectory. So the fall of the moon is the forward speed combined with the Earth pulling on it, and that curves it into an orbit. So remember, an orbiting body is a falling body. Now, how do Newton's laws play into this? Well, the moon is going to fall around the Earth essentially forever, because Newton's first law says that it's going to maintain its speed unless something stops it. A falling body or a moving body continues in a straight line at a constant speed unless it's acted upon by an outside force. Now, that explains the constant speed. Why not a straight line? Well, the outside force is gravity. So it travels at a constant speed, and the force of gravity is continually curving the trajectory into the orbit. Now, Newton's third law is that the moon and the Earth pull on each other, but remember, every force has an equal but opposite force. So the Earth is pulling on the moon, and the moon is pulling on the Earth, and it's the same force between them. The force of the Earth pulling on the moon is the same as the moon pulling on the Earth. Now, another part of this is, of course, what if we wanted something else to orbit the Earth? Would it matter if it's a space station or the moon? The moon is much more massive. The space station is less massive than the moon. But remember, all bodies fall at the same rate regardless of their mass. So the moon would fall at the same rate that the space station would fall. So it does not matter if it's a space station falling or something is the moon falling, very heavy, very light, doesn't matter. All bodies fall at the same rate. So you can see it's tying together all of these ideas, Newton's three laws, the universal law of gravitation, the concept of falling bodies, and all of that weaves together to create an orbiting body. Now, one last thing I want to show you. It is very common that you will hear the term weightless. And admittedly, NASA is actually very bad at throwing this word around without really explaining it. You will hear them say, this astronaut is weightless while he is on board the space station. So the question is the astronaut really weightless? Is he really without any weight? Well, let's explore that. Now, I'm going to show you a little bit of math here. I just want you to watch it. I won't ask you necessarily to reproduce it, but just watch as we go along here. Let's see science at work here. Now, let's say we have an astronaut on the surface of the Earth, and we're going to say that this distance from the center of the astronaut to the center of the Earth, we're going to call that the radius, and we're going to put a little subscript of Earth, meaning the astronaut on Earth, what would the distance be? So that's r. Now, let's put that same astronaut in orbit at whatever altitude that the space station happens to be orbiting. But notice the distance is bigger, so we're going to say the radius of the orbit, in this case for the astronaut in orbit. So we're going to really compare these two. We'll see how that works out. Now, what we're really after is what would be the weight of the astronaut standing on the surface of the Earth, and what would be the weight of the astronaut while in orbit. To do that, what we're going to do is a ratio. What is the force? Remember, weight is a force. If you go back a few videos, that you'll remember that weight is a force between two bodies. So what is the weight or the force acting on the astronaut in orbit compared to the weight or the force of the astronaut standing on the ground? So we're going to put in some formulas. Here is the universal law of gravitation twice, because F is going to be the same. So we're going to plug in essentially all the variables here. But here is what F equals, and here's what F also equals. But the value for R is going to be different, because remember, one of the R's is being in orbit, and the other R is being standing on the ground. Now, we're going to do some algebra here. I'm going to do the hard part for you, do all the rearranging and all the algebra for you. And so that's what we get. I know it looks, we're going to put in some variables here, right? So, and capital M is the mass of the Earth, lowercase m is the mass of the astronaut. Same thing down here. The only difference is one of them is on the Earth and one of them is in orbit. So R of Earth and R of orbit. Here's where the really kind of complicated algebra comes in. Let's sort this big old mess out here. So what we end up getting is this. So the ratio of the astronaut in orbit compared to being on the ground ends up being all of this. Now we can put in values. In other words, we know the mass of the Earth. Let's put in for the radius of orbit 200 miles. Better yet, let's make it like 200 kilometers. That's typically the altitude of anything in orbit in low Earth orbit. So the space station is about 200 kilometers up. And so, yeah, maybe 400 kilometers, whatever number you want to put in here. But what you'll find is that the radius of the Earth is a known value. So all of this is something we know. All of this is something we know. And when you put in all the numbers for this, and you multiply it by all the numbers for this, what you actually get is 89%. Now here's what that means. This astronaut's weight, while being a few hundred kilometers above the surface of the Earth, his weight is still almost 90% of what his weight on the ground is. In other words, many people think that when you are in space, your weight is now something that has gone away because they mistakenly think that gravity goes away. There is gravity in space. He has a weight because of gravity. In other words, he would fall to the Earth because of his weight, because of the force of gravity. So his weight, while in orbit, is roughly 90% of what he would weigh on the ground. Now that's certainly not weightless. So why doesn't he actually feel that weight? In other words, even though his weight is 90% of normal, why is it that he's floating or he doesn't feel any of his weight? The answer is, it's because he's falling. So the space station is falling around the Earth. The astronaut inside of the space station is also falling around the Earth. And when you fall, you don't feel your weight. You might have remembered the last time you got on an elevator and somebody presses the button, and that moment where the elevator suddenly goes down, you kind of feel like you don't have a little bit of your weight has been taken, you're a little light in the shoes at that point. So the reason why you feel weightless or having to feel a little less weight is because of that act of actually going down, of falling. If you've gone to an amusement park, any of the rides where you suddenly go downwards very quickly, it feels momentarily as if you're floating. But in reality, you're not floating, you're falling. The difference is that in an elevator, you have to eventually stop your fall, otherwise it could be very disastrous. But in orbit, you continuously fall. You don't have to stop. And so as you continuously fall, you don't feel your weight. But don't forget, he still has weight. If he were to stop his 17,500 miles per hour speed, if we made that go to zero, he would fall to the surface of the Earth because suddenly he would weigh 90% of his body weight. So the point being, here's the important part, in space you don't feel weightless because of gravity. Gravity is still there, gravity never goes away, but you feel weightless because you are falling. Falling bodies will also have the sensation of feeling weightless. So what NASA really should be saying is that there's the sensation of weightlessness rather than the astronaut is without weight. So he or she has the sensation of weightlessness because they're falling. Now remember, the last part is the space shuttle, the astronaut, everything on board the space shuttle, it all falls at the same speed. So inside of that big capsule, he feels like he's floating, but he and the capsule are falling together because all bodies fall at the same rate. So you can see that orbital mechanics is kind of complicated, but when you break it down into just some basic concepts, it really turns into being something that's understandable. So make sure you learn the bits and pieces, and then learn what it takes to tie it all together to get us this big concept that we call orbital mechanics. And so we'll be on to the next topic in the next video. I hope you'll join me.